Hello everyone, I'm Marco from Kakao Corporation Recommendation Team, and today I'm here to present our 10th place solution in Product Substitute Classification Problem, Task 3. The title of today's presentation is Predicting Query Item Relationship Using Adversarial Training and Robust Modeling Techniques. In our solution, we present a simple model and a few techniques that can be applied in any other task where deep learning models are used. I'll first briefly discuss the given problem and then our model structure, which is a simple mix of pre-trained transformers, LSTM, and multi-sample dropout. I'll also talk about some training and ensemble techniques we used to increase model robustness, which was actually our key strategy in approaching the problem. This year's KDD Cup presents the problem of having to predict the relationship between user search queries and shopping items. As shown in diagram below, if a user search query is white Vans and item name is Vans sneakers, navy, we had to classify whether the query and item were in a substitute relationship or not. An important addition to the problem is that the query is never seen before during inference, meaning any to be predicted query would not have appeared during training. So this changes the problem to predicting relationship between unseen query and an item. And this makes a big difference as shown in the next slide. Here are two training histories of same model, trained the same way but with different data split. The upper diagram is k-fold split and the diagram below is group k-fold split, where search queries are used as groups. So if there are, for example, 100 data instances with search query AirPods case, all 100 data instances would be placed in either train or test set. While validation loss decrease in quite stable manner in k-fold setting, validation loss would not decrease for a single epoch in group k-fold setting and would achieve a much lower cross-validation score. Now, despite that, it would actually reach a higher public leaderboard score as it properly mimicked the competition evaluation setting of having to predict against unseen query and item pairs. So to sum up, we used group k-fold data split with stratification on the labels as there existed class imbalance. Now for a model backbone, we used dBERTA v3 large model, which achieved highest cross-validation score among all tested models. For model input, we concat search query and item title using special token. Item title goes through a very simple pre-processing of only cleaning special characters. More intense cleaning, such as underscoring, actually led to a decrease in model performance. We improve our model structure by adding an LSTM layer after the dBERTA backbone. Note that the added LSTM layer is not pre-trained. As training finished in 1 or 2 epoch, applying dBERTA's low learning rate was not adequate and actually led to a decrease in F1 score. We initially set learning rate for pre-trained dBERTA layers to 5 to the power of -6 and LSTM layer to 1 to the power of -3, and used learning rate scheduling to decrease the rates during model training. Applying LSTM head with adjusted learning rate led to an F1 score gain. In addition, we apply multi-sample dropout for better generalization. After dBERTA's pooling layer, we add 5 dropout layers with different masks, each with a dropout rate of 0.5. Output of each dropout layers will be passed to fully connected layers, which all share the same weights. Output of all fully connected layers were then averaged. At this point, the final model structure is shown below. It is a simple model with a pre-trained dBERTA backbone, LSTM head, a pooling layer initialized using the pre-trained dBERTA weights, multi-sample dropout layers, and finally, the classification layer. We apply adversarial weight perturbation to increase model robustness. Starting adversarial training from the very beginning was most effective, instead of starting at a later period, as entire training ended in a very short period. After applying adversarial weight perturbation, training became much more stable, so validation loss would decrease for 3 to 4 epoch instead of a single epoch, and this led to a massive F1 score gain. We also calculated exponential moving average of weights during mini-batch training. We applied a decay of 0.999 when calculating new average of weights. Doing so also led to a relative micro F1 score gain. And towards the end of the competition, we changed from cosine learning rate scheduling to a step LR scheduling with decay every epoch, decayed by a gamma of 0.2. Changing learning rate schedule in such manner also resulted in an increase in competition metric. In addition to a soft voting based ensemble, a technique where model prediction probabilities are summed to get final predictions, we use a diversity based approach when selecting models for ensembling. So we ensured model diversity, as adding a different backbone with a relatively lower cross validation score actually helped increase leaderboard score. We also ensured some data diversity by, for example, validating dBERTA v3 large model on fold 0 and then training on the rest, and validating the Rambert model on fold 2 and then training on remaining folds, and in such manner. Last but not least, we use float 16 precision during inference for faster speed. Applying float 16 precision had an effect of increasing inference speed by 2.3 times compared to float 32 precision. And here is a summary of all techniques we have applied. We used pre-trained dBERTA v3 large model as baseline and add LSTM head with a different learning rate from other pre-trained layers. We applied adversarial training, which led to biggest increase in cross-validation score, exponential moving average, and multi-sample dropout. Changing learning rate scheduler from cosine to step LR schedule also led to an increase. Note that the last two cross-validation scores are same because control models for each were different. So today we discuss our approach of effectively capturing the relationship between search queries and shopping items as part of our 10th place solution in KDD Cup 2022. Built upon a solid validation strategy, we used a simple model structure of pre-trained transformers, LSTM, and multi-sample dropout to effectively predict query-item relationship. All of our strategies focus on increasing robustness of deep learning models and can be expanded to any other task that uses deep learning. Well, this is the end of our presentation. Thank you for listening.